And our today's session, we will leave the theoretical part of our lecture and will apply all the fundamentals we have learned in the last 7 days for some aspects. We will hear something from Professor Zahu about applications, and I will focus also on applications. So I will start today with the great goal reduction of carbon dioxide emissions, and we will have one lecture about safety aspects of new hydrogen applications. So what is the demand if we really want to have a hydrogen economy instead of an economy based on fossil fuels. And I think eventually on Friday, depends how fast we are, we will also discuss this topic, reduction of carbon dioxide emissions. So we may get rid of carbon dioxide, but if we still use combustion for energy production, of course there are other pollutants, and this then has to be discussed. So for the motivation, okay, we have a climate change. This cannot be neglected. Maybe on Friday we'll discuss, is it man-made or is it natural climate change? So the dinosaurs have lived in an area where we have had no ice in polar regions, so it was much hotter and on Earth at specific times. But of course, there is a strong relation between the emission of greenhouse gases and global warming. And so the actual change in temperature globally is based on the emission of greenhouse gases. And this is not only carbon dioxide. Of course, this here you see has the biggest contribution here. But there are also other emissions from agriculture, especially methane, which is a strong global warming, or has a high global warming potential. From agriculture has big contribution here. So all the cows in Brazil produce a lot of carbon of methane, which then of course absorbs radiation. We have here nitrous oxide, mainly from agriculture nowadays. But if we switch to an ammonia economy, this can change, of course. We can have much more emissions here. And here we have the F gases, hydrofluorocarbons. These are most often refrigerants, so used in our air conditioning systems. They were introduced to replace the hydrofluorocarbons we have had in the past, or so the older refrigerants where we have some problems with ozone depleting. Now we have some refrigerants which have a high global warming potential. So, and there's of course a ban of these gases, but when we look at the worldwide number or the worldwide demand for cooling systems, the demand here will strongly increase. And the question is, will this contribution of these gases to the greenhouse emissions also increase or not? So the world has the aim to stop this global warming at 1.5. I think this is no longer possible. So the next aim is then 2 degrees Celsius, but this is not the main problem. So here we talk about global warming. So when we look at specific areas, the temperature changes look totally different. In Germany, we have now much more strong rain events, and short time very, very heavy rains, which were seldom in the past. And here in India, maybe you have faced with long hot summers with periods over 40 degrees Celsius for a longer time, at least in specific areas. So this is not the so the problem plus 2 degrees is not here in the focus. The local climate change produce more problems. So there are several agreements worldwide. The idea is to change towards climate neutrality and sustainability. So we have a framework of circular economy and methods for reducing greenhouse gases. So in European Union, we talk about the Green Deal, but we have discussed it here. So there are also similar programs here in India. So you have your own strategy how to become carbon neutral until 2050, which is the global aim. So one possibility, of course, is here to use energy from renewable sources. So solar, wind power, hydro mainly, biomass maybe. So then, okay, here we don't have the word hydrogen included. So how can hydrogen contribute? So the disadvantage of electricity is that we can store it only very difficult or with high costs. There are some trends now to produce and have also larger battery storage systems. But when we look at the need we have for all energy sectors, this will be difficult. And the actual idea is to convert the electrical energy in countries where we can produce hydrogen very cheap into hydrogen from renewable sources, so-called green hydrogen, and then transport either the hydrogen directly or transfer to ammonia, methanol, methane, to species which we can handle easier, and ship the energy in this form then into the countries with higher demand. So 20 countries have already an hydrogen strategy. This is one of the possible ways how to reach a goal of carbon neutrality. So I will talk today in this lecture about safe handling of hydrogen. So hydrogen is not a new gas, of course. We know it for a long time and we have possibilities to handle it safely. But what are the challenges if we really implement a hydrogen economy? So if we can have access to hydrogen everywhere, go to our fuel station, which is then a hydrogen station, to refill our car or truck, so that not only qualified personnel come in contact with hydrogen, every one of us may handle hydrogen. So the background here is, of course, new processes need new safety concepts. So safer production, storage, distribution, and use of hydrogen in all application sectors is necessary. And this, of course, needs some research, and this will be discussed in today's lecture here. So the safe handling of hydrogen in the process industry, so is based mainly on safety characteristic data, which describes the safety issues of hydrogen. So this topic we will discuss more in detail with all the background in the next lecture. And of course, we have to talk about explosion protection. So here a classical example. So hydrogen is a light gas, so it was used in in balloons here. You may all know the Hindenburg disaster, 1937 in the US, where one large zeppelin filled with hydrogen was burning and with a lot of fatalities. Here we see an example. So this is a balloon from the US military filled with hydrogen, and it's written here that it was ignited by static caused by soldiers' hair brushing against the balloon. So everyone knows it. When you take a plastic balloon and brush it at your hair, you produce static electricity. And hydrogen, the minimum ignition energy is 17 microjoule. So this energy you would not feel on your skin if you have come in contact with such skin. And you may know, and at dry days, and if you don't have proper shoes, and you come in contact with the door handle, you feel the static electricity. And this spark there, of course, will always ignite hydrogen air mixtures. So the energy needed to ignite this is quite low, and here it was just an unfortunate soldier with his hair coming in contact to the balloon. So hydrogen is not a new gas, of course. So we have around 120 megatons of hydrogen. So it's one of the most important chemical substances we have. But of course, actually, it's mainly made from fossil sources, so natural gas, coal, and oil. So using the steam reforming process. So and only 4% comes from electrolysis, and from this, 33% is, or we assume 33% global average renewable share. In 2021, 1% of the hydrogen was green. 99% was still based on fossil fuels. So where do we use it today? So we have here two main factors. So refining in the oil industry, we need it for our proper handling of the crude oil to get finally the gasoline, the diesel, kerosene, whatever we need. And here, of course, there is also big demand ammonia production using the Haber-Bosch process. So nitrogen from the air plus hydrogen gives us ammonia, and this we use for explosives and mainly for fertilizers. So, and then of course here we have other demand in chemical industry, but these are the two main parts, and actually 120 megatons of hydrogen. So here you see an example. So BASF was once the largest producer of hydrogen in Germany. Now they have shut it down and eventually will rebuild it somewhere else because energy is quite expensive nowadays in Germany. But here was around 1 megaton of hydrogen produced in this chemical plant. And I'm not aware of any accidents with respect to hydrogen in the last 50 years here at BASF. So accidents with hydrogen occur, of course, but they are quite seldom, especially in the bigger chemical complexes, because we have a strong regulation here in Europe. We have the so-called ATEX directives, which deals with safety at work mainly. So the existing regulations fully covers fully cover hydrogen. So there is no demand of any new or stricter regulation. But we also have to know that hydrogen is produced in closed areas where only well-trained personnel has access. So the experts here know how to handle this and are aware of the danger when you deal with hydrogen. So this also we will discuss more in detail with the next lecture, but when we consider explosion protection, we have a combustible, we have a heat source as an ignition source, and we have an oxidizer, so mainly oxygen from air. And if we have this in proper composition, then an explosion may occur. So we have several measures to avoid this. First of all, we want to avoid the formation of an hazardous explosive atmosphere. That means here we try to limit this or this here. Secondary explosion is we want to avoid an ignition source, so we focus more on this part here. And tertiary explosion protection, okay, we want to reduce the effects of an explosion. Use, for example, flame arresters and so on. So we have a classical classification of areas here to handle the danger properly. So we have a zone 0 for flammable gases and liquids, and 20 for flammable dust. So in this zone 0, 20 we have permanently or frequently hazardous over a long period. And then this probability reduces, so then we have a zone 1 where we have occasionally, which is occasionally hazardous, and we have a zone 2 where we have seldom hazardous atmospheres. And here we see in draft sketch, here we have our tanker. Inside this we have a zone 0. There's nearly always a hazardous atmosphere. And then near the filling station here, we may have a zone 1, and then in some distance a zone 2. And then you need to use proper equipment in these areas. So these have to be tested by notified bodies. And we have different categories here. And for hydrogen, so mainly we talk about these two zones here. Zone 1 and 2, because it's quite expensive to have electrical equipment in a zone 0, especially when you deal with hydrogen. So how do we classify then the gases we have? So we have 2 explosion groups, or 3, sorry, now 3. So the first one is mining only. So we have specific safety requirements for mining area. Then we have explosion group 3, where we talk about dust. And the focus today here in this part is, of course, group 2, which we divide into 3 groups, 2A, 2B, 2C. And this is done, for example, with the maximum experimental safe gap, which is quite large for 2A and much smaller for group C. So we will discuss this topic today in the afternoon or tomorrow more in detail, so give you all the background here. So maybe easier to understand is here the minimum ignition energy, which we also can use to separate the gases. So gases of group 2A, as an example, propane has a quite high minimum ignition energy of 0.2 millijoules. and this goes down to the group 2C, hydrogen and acetylene, where we have ignition energies below 0.05 millijoule. And just as an example, ammonia has a minimum ignition energy of 14 millijoule. So it has nearly 100 times this value here. But nevertheless, it can be ignited and of course can burn ammonia in air. Another topic is the temperature category, which we use in explosion protection. So you see here different temperature classes, T1 to T6, and so the maximum permissible surface temperature of equipment has to be below 450 degrees down to 85 degrees Celsius. What is the idea behind this? So the gases which or the combustibles which can in contact with our equipment here have an ignition temperature, an auto ignition temperature. Again, this we will discuss later. And of course, different gases or combustibles have different ignition temperatures. So here you see that these gases, these combustibles here on this line, have ignition temperatures larger than 450 degrees Celsius. So you can use equipment of temperature category T1 safely with these gases because the ignition temperature is higher. So and that's reduced down to T6, where we have only carbon disulfide. And interestingly, the ignition temperature of hydrogen is quite high. So 595 degrees Celsius. I have to check literature again. So it has a really, really low ignition energy, minimum ignition energy. But the ignition temperature is quite high. So this is a big advantage here if you want to handle hydrogen. So we characterize combustibles with safety characteristic data. Again, this we will discuss more in detail later. So first of all, they are no material constant like boiling point, but they give us quantitative information about material properties. So as we have seen, group 2A, 2B, 2C. So we know group 2A combustibles are safer, easier to handle than group C combustibles. They are not independent of the determination method. You will see differences when you look in literature. Minimum ignition energy for hydrogen in Europe maybe is tabulated different compared to minimum ignition energy here in India. You may find other values, but you are not always in the same range. The main problem is, again, we're talking about safety at work. Most of the data we have is for atmospheric conditions. So minus 20 to plus 40 degrees Celsius and 850 to 1100 millibar. So if we are out of this atmospheric condition, we cannot use the existing data to discuss safety topics. We have to measure them or to yield them again. Here's the antennary diagram of the explosion region of hydrogen, which is here. Inert gas, nitrogen here, and oxygen here. So I'm not sure if you are aware of these kind of diagrams, but the idea is we can determine the exact mixture composition. So oxidizer, inert gas, and flammable gas at every position in this diagram. And here we see hydrogen. Hydrogen has a lower flammability limit of around 4% and an upper of around 78%. So these are the flammabilities in air and in oxygen. So and then in air, sorry. And then here we see this curve here. So if we add nitrogen to this mixture, we of course strongly change the upper flammability limit, while the lower flammability limit more or less stays constant. So, and mixture composition inside this region are explosive, combustible, and mixtures outside are not combustible. So there's one interesting effect that is the lower flammability limit with 4% is quite low, and so we can see this when we, for example, calculate the laminar burning velocities of hydrogen. So you see below 10% hydrogen, we nearly reach zero. Nevertheless, the flammability limit here is around 4%. So we have here, for example, diffusive preferential diffusion effects. So the hydrogen is moving towards the hot flame, and so inside the flammable region, there we have locally higher hydrogen concentrations. So hydrogen is a light molecule, diffuses very fast. This strongly supports then the combustion process. So this can be seen here when, for example, measure the pressure after ignition in a closed vessel. So with 3%, there is no pressure rise. This maybe was ignited by a spark, but no self-sustaining flame propagation could be observed. With 4%, some reactions occur. But if we already have 6%, we already have an explosion pressure of around 2.2 bar. So here, of course, we already have strong reactions. This I will discuss later with one slide more in detail. So minimum ignition energy, I said to you, so 17 microjoule, very low. But here we have to consider, of course, if we have richer or leaner mixture, the energy is much higher. We need to ignite the mixtures. And when we talk about the 17 microjoule, this means that in 1 of 100 experiments, such a spark has ignited hydrogen. So we are talking about an ignition probability which is quite low, giving up this low value. But one important topic for hydrogen is, so here you see this classical probability curve we use when we perform here ignition experiments. So we see an ignition or see not an ignition. So also if we, of course, use the same energy, it can happen, it ignites or it does not ignite. This for classical hydrocarbons covers normally a broad range with respect to energy, and this range is very small case of hydrogen. So hydrogen really is interested in getting ignited and start combustion. So let's see if these videos are working. So here we ignite hydrogen between two sparks, or between two electrodes, and what you see that after the ignition, all four videos more or less look identical. So Here we have varied the ignition energy, so from 2.3 up to 5.6 times the minimum ignition energy. And so we are already in a range of 99% ignition probability here. So it's quite high, and when we look at it in detail, you can see that the lighter one seems to be faster. So compared to this one here, so it reaches at earlier times the outer boundary of the video here. But it's not faster. We just have deposited more energy into the system. So the initial kernel is a little bit larger. The ignition occurs more or less at the same time. And then we yield constant flame propagation with a constant flame velocity. And we have performed the experiment several times for specific energies, and you see only small deviations here. So it's very stable, this process, and the difference here comes from the different energies we need, but there was no difference in ignition delay time also. An interesting effect here is we have a mixture of 23% hydrogen. It's a lean mixture. This is the most ignitable mixture. And here the Lewis number of hydrogen is smaller than 1. That means again the hydrogen is moving towards the hot zone due to diffusion. And so when we deposit the electrical energy and we start the combustion process, it is moving towards the zone. And one another important topic is we have, of course, strong curvature at the beginning. We have a very small ignition volume with strong curvature. And in case of hydrogen, this enhances the flame propagation. So if we ignite it properly, we will always will see that it develops to a bigger flame ball. Then we have this maximum experimental safe gap, which I will explain in the next lecture more in detail. But you see here, hydrogen has a broad explosion region compared to the other gases, and of course has much lower ignition energy. Another nice aspect, so this is based on, I talked about ignition energy, of course, means safe gap. Safe gap means the flame has to move from this volume to the outer volume, and the width of this gap depends is there a flame transmission or not. And in case of hydrogen, this can be much smaller than in case of the other combustibles here. So, and when we look here into the details, so we see here such a flame transmission now to a through nozzle, and we have identical configurations. Yes, wherever you want. Thank you. So we have identical configurations, but in this case it ignites directly at the nozzle. Here it takes some time to reignite, much further downstream, and in the third case it does not ignite. So of course when we talk about turbulent flow, we have a lot of other statistics to consider, so which then of course influences the ignition probability. Then we have to talk about explosion pressure. So as we have seen yesterday, so the adiabatic flame temperature of hydrogen is around 2200 K. So when we look at the ideal gas law, so the pressure change comes from the temperature change. We start at 300 K and at 2100 K, so we have a factor of 7. So we expect a pressure increase of a factor of 7, which matches here. So normally we do these experiments in a sphere to determine the maximum explosion pressure. So the explosion is in the center of the sphere, and we have a spherical flame propagation. So any wall effects can be seen very late only, so we yield the maximum pressure, and then we have cooling at the walls and so on. When we perform such an experiment in a cylinder where we ignite at one end, of course we see a different pressure curve as a function of time. But you see we nearly reach the same maximum pressure. So the cooling effects, due to the fact that the flame has to propagate in this way, and we have a lot of wall contact, is nearly neglectable. So hydrogen burns so fast that the cooling for this configuration is not of interest. But what happens if we have more complex geometries? So here we have, for example, two tubes, and between these two tubes we have an orifice. And so we ignite here, and we have measured the pressure in both vessels. So here in this vessel, when we ignite here, we see more or less the same pressure as a function of time. But what is happening? So we ignite the mixture here, temperature increases, pressure increases. So and with this expanding flame, the pressure is increasing until the flame reaches this nozzle. And there is a given pressure difference of maybe here in this case nearly 4 to 5 bar. And this pressure difference, of course, means we have an acceleration of the hot gas into the second chamber. So we get a large turbulent jet. This we have also seen yesterday. And then, of course, we have very fast combustion due to the turbulent flow we have. And in addition, we have ignition in a very large volume. So the combustion here is very, very fast. And that means we start at higher pressures due to the fact that the slow combustion process here already moved a lot of gas in the second chamber. And the combustion here is so fast that there is no pressure relief to the first chamber. So we need much higher pressure. So in this example, nearly 15 bar, but with proper configuration we reach 35 bar. And in complex test samples, in our test field, we also have reached 100 bar. And we assume we have not had a detonation here. It's always the so-called pressure piling. We increase the pressure before ignition. So we start at a higher initial pressure and reach also then higher end pressure. And then here we see some sound waves. This we do not have to discuss. Detonation. You may know this accident from Fukushima, 2011. So where we have after a tsunami several accidents in a nuclear facility, and So after the flooding, hydrogen was produced inside the nuclear reactor, and after an ignition of these hydrogen, heavy explosions were visible, so detonation has occurred. And the problem here is that a detonation appears not instantaneously. So after ignition, we first have a deflagration, and then it needs a proper conditions to get a detonation. And for methane, for example, it takes around 10 meters after ignition until we may reach proper conditions for detonation. So the flame has to develop for a very long time and should not be disturbed. In case of hydrogen, we talk about 10 centimeters. So it, of course, occurs much faster, much earlier, with then much higher consequences. And here you see an example where we have an unconfined hydrogen explosion. So here we have more or less plastic foil, so this should not hinder or should not result in much higher pressure here. And inside this large hemisphere, there were some internal constructions to enhance the development of turbulent flow. And so we see already a detonation for this example, which is quite seldom for hydrocarbons. So hydrocarbons and detonations, we are talking normally about pipes. We need something like a confined equipment where we can get this detonation. The only example I know is Barnesfield disaster, where they also talk about detonation effects, and where we have had an unconfined hydrogen air explosion. One of the interesting parts is here the TNT equivalent is quite high. That when we compare the strength of a hydrogen detonation with a TNT explosion, here we have a factor of 28.65. So it's 1 gram of hydrogen corresponds to 28.65 gram of TNT, which of course is a well-known explosive. So this curve we have already discussed in details. So when we look at the ignition limits, here this classical limit curve, temperature or pressure and temperature, we have different kinetic and diffusion effects which we have discussed, and this is then the advantage of hydrogen. At around 1 bar we have a quite high ignition temperature. Here the kinetics helps us. So we have only slow reactions taking here place at these low temperatures. So with HO2 and with H2O, and so the prominent reaction H plus O2 giving OH plus O is important at much higher temperatures here in this region here. So here that's the advantage of hydrogen. Even though we can ignite it very easily, the outer ignition temperature is quite high at standard conditions. So, okay, we know how to handle hydrogen, we know about the danger, so where's the problem? And so you see, this is how we handle it in Europe. We have a happy hydrogen molecule jumping over a green field, so everything is fine. So some birds are missing here for the perfect atmosphere. But of course, this is not what is the reality. So actually we have a very positive opinion about green hydrogen and the developing a hydrogen economy in the public or in the community. But of course, we have to consider that this public acceptance can change after an accident. Then we have to think about regulatory requirements. So if we use hydrogen everywhere, what has to be changed? Do we have a safe infrastructure for this? What is necessary for standardization and what is necessary for education and training? So concerning educations, okay, this is unfortunately in German because it's from a German website. This is from a TÜV. So TÜV is normally well known, thank you, for safety assessment. So they have a strong background, and written on their website was, okay, we can ignite hydrogen at 4% with an amount of 4% in air already, so the lower flammability limit. But what they say is, okay, until we reach 18% of hydrogen in air, there is no explosion danger, which is of course completely wrong. I think they mean this is maybe the lower detonation limit. So mixtures below 18% may not detonate, but I think I have shown it to you. Maybe we'll see it later. Also, lean mixtures result in strong pressure rise. So this is totally wrong. Another very common opinion is hydrogen is much lighter than air. So if there is a leakage of hydrogen, it's outside, we do not have to bother about this. It's going up, it vanishes, so everything is fine. This is of course also not correct. Another statement from a chip manufacturer who does not want to handle with safety aspects was ammonia does not burn. So ammonia is a typical hydrogen carrier. So he wants just to save some money, and he just said, okay, under standard conditions, this does not burn. It has a minimum ignition energy, it has flammability limit. So of course it burns under standard condition, even though it burns quite slow. And this is from a website from a manufacturer of storage devices of hydrogen. So also someone who should have some experience. And there was written, so is hydrogen explosive? No. So of course we know it's not explosive. So hydrogen air mixture is combustible but does not explode. A mixture of hydrogen and pure oxygen is explosive. So you can write this on your website, but it's, I think, not correct, even though they should have some background here. So of course, here we have to take care that we have proper education, that we get rid of this nonsense here. Public acceptance. Here is a hydrogen station in Norway. There was an accident, so there was a rupture of a flange of the high pressure tank, sudden release of hydrogen, auto ignition event, a small explosion and some fire. And here we have a roundabout, and so due to the explosion, some parts flown on this bikeway, and in this roundabout I think one airbag has opened, and therefore there was one injured person due to this airbag opening. So nothing more has happened. But the outcome was that for a very long period, hydrogen stations in Norway were closed, and also some of this company in Germany. So if you have just bought a new fuel cell car, with demand of hydrogen, and suddenly there is no filling station. It's complex. And after analyzing this, I think there is a requirement in Norway that there is a given distance of several hundred meters from the filling station to the next building. So it's, of course, then quite difficult to find a proper location when you need to, for example, 500 meters minimum distance to the next building. So even though it was only a very small accident, the outcome was quite heavy. And this, of course, does not support change towards a hydrogen economy. Regulatory requirements, okay, I will not go into all the details, but the US, for example, okay, with the last or the existing president, this may change with the next one again, but they have had the Inflation Reduction Act, and they invested a lot of money into renewable energy usage, so that means also in hydrogen. So in total here, 370 billion US dollar. In Europe, we have a lot of regulations. For example, we have a ban of combustion engines in cars, and here we have it for heavy-duty vehicles. So they should reduce their emissions by 90% by 2040, and city buses will have to be zero emission by 2030. So this is given by the EU regulation, and then no one knows how to handle this. Well, that's, of course, typical way how you have to handle with politicians. And then the next problem is there is no strict regulation. So in February 2023, after a very long time, finally there was published the revision of the Renewable Energy Directive, which is, of course, for manufacturers and end users necessary that they know how to deal with this possible change towards a green economy. So it needed 3 years to provide a framework here in Europe which defines the renewable-based hydrogen and hydrogen-based fuels. So of course here we have to be much faster. Otherwise, if we do not accelerate the regulatory requirements, it will be difficult to come towards a hydrogen economy. But okay, what is the real problem? So here we have to talk about the numbers. So the primary energy demand worldwide in 2022 was 170,000 terawatt hours. So mainly here in Asia. So 1.4 billion people living in India. They need, of course, some power and so on. And the rest of the world also has, of course, a demand. When we look into Germany in 2021, okay, here the green, there was still some production from nuclear power, but of course you see when you compare it with the other numbers, already negligible at that time. And we have 905 in gas, 588 in coal, and nearly 1,200 in oil, but already 571 in renewables. And this is a total primary energy demand for all sectors. So here, this is then the final energy. So we have the different sectors here. We have industry, we have households, we have smaller companies and other topics, and we have mobility here. So these are the four main sectors. And the idea in Germany is to have this and this, so blue, dark blue and yellow, covered by renewable energy production. So with mainly using electricity. So battery electrical vehicles and heat pumps for households. And this is possible when we look at the numbers. So here we have the public net electricity generation in Germany in 2023. Still a huge number coming from nuclear energy, around 1.6%. And already here 60% coming from renewables. And in northern Germany, we already have 75%. So this is so it will be possible. Of course, here we have to install more PV and wind parks, but this can be increased. Then we have only the problem, of course, of energy storage, because especially in winter, we won't yield these numbers at all times. So we need to import energy. And when we just make a rough assumption with the numbers, so we need around 2,000 terawatt hours for net zero emission. So that means this is approximately 60 megatons of hydrogen per year. To produce 1 megaton of hydrogen, we need 50 terawatt hours renewable energy, assuming a 67% efficiency. So we talk around 3,000 terawatt hours. And that means, well, again, assuming 5,000 hours per year working time for the mainly PV and wind parks, we need 600 gigawatt electrolyzers. So then when we look at our national hydrogen strategy, we are talking about an installation of 10 gigawatt in Germany. So we can, of course, use electrolyzers to store energy, electrical energy, which we not need at that specific time in hydrogen, but we cannot fulfill the needs we have in Germany with all the renewable energy sources. So we always will have to import hydrogen. Here we talk about 60 megatons per year. Just again, in comparison, actually we produce 1 megaton hydrogen in Germany per year, and this are in total 1.8 megatons. So this means there's, of course, a strong demand of energy carriers. And so we have this renewable energy, we have electrolyzers, and then we can produce hydrogen, and from this ammonia, methane, methanol, and this has to be transported to the end user. So everything looks easy, but again, when we look at the numbers, maybe we will have until 2030 10 megatons production, 10 megatons per year import. So this, again, Germany needs around 60 megatons to reach net zero. So in 2030, there is only a small step achieved. The worldwide demand, of course, depending on different scenarios, is 500 to 800 megatons. green hydrogen. And remember, actually we have 120 megatons, and only 1% of this is green. So from one megaton green, we want to go up to 800 megatons green. So, of course, there are different possibilities, different scenarios, depending on different sources here. So we have actually everything is gray, and in 2015 everything is green, or we have green plus blue hydrogen. That means we use carbon capture, utilization, and storage. So this is a big step, of course. A lot of investment is necessary. But so when we look at the costs of hydrogen in different regions, so we can see here, red means low costs, and specific areas here in Chile, here in this area, maybe also in, not maybe, but also of course in some areas here in India, the cost per kilogram hydrogen are quite low. So we can produce hydrogen here in these regions quite cheap. Nevertheless, 65% of the demand is here and here and here. So this, of course, will change the transportation sector, but I always say we have this already with our oil and gas industry. So oil is produced here and in other areas and consumed in the northern hemisphere. So there is maybe a change away from fossil fuels to hydrocarbon. And when we look at this map here, we see that there are a lot of investments already going on in the world. So, okay, Europe, we want to produce around 10 megaton per year. Also, and in Spain especially, there are a lot of plants already. I was in Tunisia and in Namibia, and we have plans with Colombia and Chile. So there's also big interest and some investments. And here, you may know this country here. Also, a lot is happening here in India. Yes. You have your hydrogen strategy, and at least you install a lot of PV, which you may use for hydrogen production for export, in my opinion. But then the question is, of course, we have to define the product requirements. So we have to be sure that there is not a big a coal plant here producing electricity, and then this electricity is used to produce green hydrogen, which then is exported to Germany, for example. So this, of course, is critical. If you compare hydrogen from fossil sources with green hydrogen, you can see difference in the molecular fingerprint. So the ratio of protium to deuterium is a hint. But if you use a gray power plant to produce electrical power and then an electrolyzer, that you cannot separate it. So we need, of course, proper certification for the acceptance here. So the PTB where I'm working is dealing here with different countries. So we have energy partnerships from our Ministry of Economical Affairs, and we have projects with energy focus from our Ministry of International Cooperation. And so here we see India. There are projects with PV projects, but of course in the future, hopefully, we will also have some projects with hydrogen. So, and this is a beautiful future we are talking about. So, in Germany, so some chips with green hydrogen, green ammonia, green methane come to our shores. The energy carrier is put into our system here. We produce locally some hydrogen and put it to the system. We use it in filling stations, we use it in industry. So everything looks quite nice and blue here. But of course, when you look into the details, you will see some problems here. I look at the clock, so I think we make a break now for 15 minutes. And we'll continue at 11:30, okay?